Hi friends, welcome to my channel Interesting Engineering. In our video, we are going to discuss about moving iron instruments, MI instruments. So, in our previous video, we have discussed about PMMC instruments. So, what's the difference between a PMMC instrument and a MI instrument? These two instruments are meant for measuring the values of currents and voltages. The basic similarity is the thing it is meant for measuring the currents and voltage values. But what's the difference between these two instruments? So in the construction part also it differs, and in the application part also it differs. The major difference between these two instruments lies in its application point of view. The PMMC instruments, that is nothing but the permanent magnet moving coil instruments, are meant for measuring the DC values of currents and voltages, whereas the MI instruments are meant for measuring both AC and DC values of currents and voltages. Regarding its constructional part, in the case of PMMC instruments, the moving element is the coil, whereas in the case of MI instruments, the moving element is nothing but the iron piece. And the second major difference is the magnet. In the case of PMMC instrument, we make use of a permanent magnet to create magnetic field, whereas in the case of MI instruments, we make use of electromagnet to produce magnetic field. These are the major differences between a PMMC instrument and a MI instrument. So let's see about the MI instruments. The MI instruments operate on a simple concept. Normally we would have known when we place a iron piece in a magnetic field, it gets attracted. So that's the basic concept behind a MI instrument. So that is the principle the MI instruments make use of. Let's see about its construction first. So in the case of MI instruments, there are two types of MI instruments available. One is the attraction type moving iron instruments, and the second type is the repulsion type moving iron instruments. So first we shall see about the attraction type moving iron instruments. So here when we look at the diagram, we have a flat cylindrical structure which is bounded with number of turns of copper coils, and in this flat cylindrical structure we may place a moving iron. It's in the form of a disc shape. So this disc shaped moving iron is placed in the magnetic field developed by the coil. So coil here acts as the electromagnet. When we pass current through the coil, it gets magnetized. So that magnetic field, in that magnetic field we are placing the disc of iron piece. So with that iron piece we are connecting a pointer over here, and here we make use of a balance weight and a control weight arrangement to produce a controlling torque here. And here there is a air chamber. This air chamber is meant for providing a damping. So as usual, similar to the PMMC instrument, these MI instruments also consists of 5 main parts. The 5 main parts are magnetic arrangement, moving system, then the controlling system, damping system, and the indicating system. The magnetic system, here we make use of a electromagnet. So to have a electromagnet, we make use of a coil. Number of turns of copper coils are wound over a cylindrical structure, and that coil, the current through that coil produces a magnetic field. In that magnetic field, the moving system is nothing but the soft iron disc. So that acts as the moving system here. to have a controlling arrangement, to produce a controlling torque, we make use of a weight. The weight is placed nearer to this moving iron arrangement. So this controlling weight will produce a force in the opposite direction to that of a deflecting torque. And to provide damping is meant for reducing the oscillation of this pointer arrangement. We make use of damping. So that damping is provided by means of this pneumatic arrangement here. So these are all the 5 main parts. So what are all the 5 main parts? One is the magnetic system, second one moving system, third is the controlling system, fourth is the damping system, and the last comes the indicating system. So the moving system here is the soft iron disc, and the magnetic system is the electromagnet, which is obtained by means of passing current through the coil wound around a cylindrical structure. Third one is the controlling torque, which is obtained by means of a spring balance. The counterbalance that is operated by means of a control weight placed over there. And the last damping arrangement, we make use of pneumatic damping here. So to achieve the pneumatic damping, there is a piston connected with the pointer arrangement. This piston moves in a air-filled chamber. So by the movement of this piston over the air-filled chamber, we could able to provide a damping torque to the pointer movement. And the last comes the indicating system, which is nothing but the pointer and scale arrangement here. So this is the diagram, this is the constructional part of the attraction type moving iron instruments. So here what's its operation? So in the case of its operation, we make use of current here through the coil here. So the amount of current or voltage that is to be measured is passed through this coil, and based on that intensity there develops magnetic field. So the magnetic field strength depends upon the amount of current passing through the circuit. And here there is a iron disc. So this iron disc gets attracted towards the magnetic field from the weaker section to the stronger section. So that is based on the intensity of the magnetic field. The intensity depends upon the amount of current or voltage entering into the coil. So this moving iron will be attracted. So based on its attraction, based on its movement, the pointer connected with this moving iron will also gets deflected over the scale arrangement. So that is nothing but the deflecting torque. So that deflecting torque has to be balanced by means of this controlling torque provided by the weight arrangement placed at the bottom of the moving iron here. So this controlling weight will produce a opposing force to that of the deflecting torque developed here. So that makes the pointer to come to a steady position, and though it provides a controlling torque, the pointer will have little bit of oscillations. So that oscillation can be controlled by means of damping arrangement provided here. So the amount of deflection of the pointer depends upon the movement of this moving iron. The movement of this moving iron depends upon the voltage or current passing through the coil. So the amount of deflection will be directly proportional to the amount of current or voltage entering into this coil. So that's about this attraction type moving iron instruments. So I have given the construction as well as working in a 3 points here. It consists of iron disc placed in the magnetic field produced by the current passing through the coil. Based on the strength of the magnetic field, the vane moves from lower magnetic field to higher magnetic field. Due to the movement of the vane, the pointer attached to it also gets deflected, and it is the measure of the current. So this is about the working of attraction type moving iron instruments. Then comes the repulsion type moving iron instrument. So here in the previous type there develops attractive force, but here there develops a repulsive force. So based on that repulsive force the pointer will be operating. So here too there is a iron piece fixed vane. This fixed and movable vane, it consists of two soft iron pieces, and among those two soft iron pieces, one is the fixed one and the other one is the movable one, and these two iron pieces are polarized with same polarity. And this fixed and movable vane is placed in the magnetic field developed by the current passing through the coils. So here too we have a cylindrical arrangement here, and to that cylindrical arrangement there is placed a number of turns of copper coil to which we are passing the amount of current that is to be measured. Based on the current entering into the coil, there develops a magnetic field. In that magnetic field we are placing two soft iron pieces, and one is the fixed iron piece and the other one is the movable iron piece. To the movable iron piece we connect a pointer over here. So based on the movement of this movable iron piece due to the repulsion, that is these two iron pieces are with same polarity, and when these two iron pieces are placed in the magnetic field it gets repelled away, because we all know the magnets, iron pieces with same polarity, magnets will be attracted with a different polarity. With same polarity it will be repelled away. So based on that concept, this movable vane will be repelling from the fixed vane. So due to that there will be some movement of this movable vane. Since the pointer is connected directly with the movable vane, the pointer will also gets deflected. So based on the amount of magnetic field developed here, the movable vane will be deflecting. So that deflection makes the pointer over here to deflect. So this deflection will be directly proportional to the amount of field developed. So this magnetic field developed based on the amount of current entering to the coil. So this is the operation of a repulsion type moving iron instruments. So here similarly I have explained here, it consists of two iron plates or vanes in a magnetic field, out of which one is fixed and the other is movable. Both the vanes are polarized with same polarity. When the coil gets magnetized due to the passage of current, the movable vane gets deflected, and hence there occurs deflection of pointer, which is the measure of quantity of current flowing through the coil. So now we shall derive at the torque equation of MI instruments. So before entering into this derivation, let's see about how does it operates and what are all the terms involved in its operation. So initially we are passing some amount of current that is to be measured into this coil. So this coil gets magnetized and it acts as an electromagnet. And when a soft iron piece is placed in this magnetic field, it gets attracted over this magnetic field. So there will be some sort of movement in this iron piece. So the pointer that is attached with this iron piece gets deflected, making an angle theta. So that acts as the deflection. So the deflecting torque is developed by means of this movement of iron piece. So whatever the energy supplied from the source is stored in this inductor in the form of inductance, and it creates some sort of work done on the pointer to deflect. So these are all the terms involved here. So what the energy that is supplied from the source is stored in the inductor and it creates deflection. in the pointer. So that we are going to represent it by means of mathematical equations. So before entering into the equation, we shall know what are all the terms involved here. So let I be the initial current through the coil. For over a time period, it changes from I to di. So I plus di will be the change in current in the coil. The inductance of the coil will be L, and due to the movement of iron piece, the inductance increases, so it changes as L plus dl. So due to the change in inductance, that creates deflection of coil theta. So the energy stored in the coil, we can represent it as E is equal to 1 by 2 Li square, which is nothing but E is the energy stored in the inductor, L is the inductance of the coil, and I represents the current passing through the coil. So due to the flow of current in the inductor, in the coil, there occurs change in the stored energy, and it can be represented as change in energy will be equal to 1 by 2 into L plus dl into I plus di the whole square. So what will be the resultant change in energy? So the resultant change in energy will be represented as delta E, and it is equal to the change in energy minus the energy stored in the coil. So it can be written as 1 by 2 L plus dl into I plus di the whole square minus 1 by 2 Li square. So I am expanding this equation. Since it is in the form of a plus b the whole square, I have expanded it in the next step as I square plus 2I di plus di square. The other things remains the same, just I am expanding this equation. So I square plus 2I di plus di square minus 1 by 2 Li square. So in our next step, I have multiplied it once again. So in both these terms, 1 by 2 remains constant. So I am taking it outside. L into I square is Li square. L into 2I di will be 2 Li di, and L into di square is L di square plus I square dl plus 2I di into dl plus dl di square minus this half 1 by 2 is taken outside, so I have replaced it here, Li square. Then in the next step I am eliminating the higher order terms. So here when we see at this equation, we have this di square dl, these are all the higher order derivatives, so I can eliminate it. So then this Li square, here we have plus Li square and this is minus Li square. So on eliminating these higher order terms, the resultant energy will be delta E is equal to 1 by 2 into 2 Li di plus half I square dl. So resultant delta E, resultant energy stored will be Li di plus 1 by 2 I square dl. So what is the energy supplied from the source? What by passing current through the coil, what is the amount of energy supplied from the source? Let's calculate it first. So the energy from the source will be EI dt. So here what is E? E is nothing but the potential developed. So here since we have a coil, the E will be written as E equal to d by dt of Li. So L is also changing and I is also changing. So I am writing it as, when we differentiate this equation, we have it as I into dl by dt plus L into di by dt. We need EI dt. So on multiplying this entire equation by I dt, we get it as I square dl plus Li di. This is the energy from source value. Then what's the work done? Work done is nothing but theta, deflection of the pointer by means of the deflecting torque. So it can be represented as work done equal to Td into d theta. As I have said earlier, the energy from the source is equal to the energy stored in the inductor plus work done for deflecting the pointer. So the energy from the source we have already derived it here as I square dl plus Li di. So I am replacing the energy from source as I square dl plus Li di. The energy stored, we have derived that equation to delta E equal to Li di plus half I square dl. So I am replacing it here. Then work done is nothing but Td into d theta. So on equating these equations, we have in the next step, in our equation we have Li di on both sides, so I am cancelling it out. So it is changed as I square dl. I am bringing this half I square dl to the other side. So I square dl minus half I square dl is equal to Td into d theta. We need the deflecting torque value. So I am keeping this Td on one side and bringing all other terms to the other side. It changes as Td equal to 1 by 2 I square dl by d theta. So this is the equation for deflecting torque in MI instruments. So Td is nothing but the deflecting torque is equal to 1 by 2 I square. I is nothing but the current value. So the current passing through the coil, and it changes the inductance and deflection of the pointer. So the deflecting torque is equal to 1 by 2 I square dl by d theta. For any instrument, there develops three different torques: deflecting torque, controlling torque, and the damping torque. So whenever the deflecting torque gets equalized by the controlling torque, the system will remain in a steady position. The controlling torque is achieved by means of the spring arrangement provided. So Tc is equal to K into theta, where K is nothing but the string stiffness and theta is the deflection of the pointer. So when we equate these Td and Tc, we get it as 1 by 2 I square dl by d theta is equal to k theta. So we need the value of theta here, that is nothing but the deflection of the pointer is equal to, when we bring all other terms to the other side, k comes to the other side, so it changes as theta is equal to 1 by 2k I square dl by d theta. So here the deflection theta is nothing but directly proportional to the square of current value entering into the coil. So this is about the torque equation of the MI instrument. So in MI instrument, the amount of energy supplied from the source is stored in the inductor in the form of energy, and it also makes the iron piece to deflect at a certain angle theta that we have expressed using this equation. The energy from source is equal to energy stored plus work done. So what is the energy from source? We have derived by using the equation Ei dt, and energy stored is obtained using this expression Li di plus half I square dl, and work done is nothing but the work done is due to the deflecting torque, and it makes the deflection of angle theta. So on equating these terms, we get it as theta is equal to 1 by 2k I square dl by d theta. So the deflection of the pointer is directly proportional to the square of RMS value of current entering into the coil. So this is the operation of a MI instrument. So now we shall discuss about the advantages and disadvantages of MI instrument. So now we shall say about the advantages of MI instruments. So these MI instruments can be made use of for measuring both AC and DC quantities, and the cost of this instrument is also very less. It will have a less friction error because here we make use of iron pieces as the moving element. Since these iron pieces are of smaller in size, there will be less friction due to small moving parts. Then comes the disadvantages of the MI instruments. Here, when we look at the torque equation, the deflection is proportional to the square of current value of the square of current value. So based on that, we have a non-uniform scale arrangement. So it doesn't produces a highly accurate output. There also occurs error due to frequency variations and stray magnetic field variations. So this is about MI instrument. So these MI instruments, in these MI instruments, the moving part is nothing but the iron piece, and the magnet used here is the electromagnet. Based on the intensity of the magnetic field, there occurs deflection, there develops a deflecting torque, which is indicated by means of a indicating instrument. So this is about MI instrument. We shall see about the electrodynamometer type instruments in our next video. So for more videos, keep watching. Please subscribe and share. Thanks for watching.